Okay, in this video I'm going to continue on with exercise 7a of the book Fundamental Applied Mathematics. We're on page number 172 and the question is 11. And we're now on to the honours question. So this reads, a ring of mass m is threaded over a taut horizontal wire. The ring is attached to a bead of mass m by a taut inelastic string of length 5 meters. The system is released from rest in a horizontal position. Find the speeds of the ring and the bead when the string is vertical. Now, of course, we can start applying Newton's laws and so on here. However, the point of these chapters is that we're going to employ the principle of conservation of momentum and the principle or the law of conservation of energy to solve these. So how do we do that? Well, we have two scenarios. First of all, when the bead is parallel to the wire, and second of all, when the bead is perpendicular to the wire. So let's go ahead and solve this. So what I'm going to do first of all is employ the principle of conservation of momentum. Alright, so let's just do that. So we get the mass of the ring, which is m, times the initial velocity of the ring, which is 0. Plus the mass of the bead, which is m, times the initial velocity of the bead, which is 0, is equal to the mass of the ring, which is m, times the final velocity of the ring, which I'm going to call as v1, plus the mass of the bead, which is m, times the initial velocity, or the final velocity of the bead, which is v2. So we're going to find that mv1 is equal to negative mv2, or you can say that v1 is equal to negative v2. Alright, so if the bead is going to the left at a certain magnitude, then the ring is going to the right with the same magnitude. That's what that means. Okay, so the next thing we need to do is apply the principle of conservation of energy. Remember, the principle of conservation of energy needs velocities. So we have the initial velocities at this stage. So what I'm going to do is as follows. I'm going to have the principle of conservation of energy, or the law of conservation of energy, excuse me, at position 1 is equal to the law of conservation of energy at position 2. Alright, so let's go ahead and do that. So we'll say the ring, we have the potential energy plus the kinetic energy plus the bead, the potential energy plus the kinetic energy, and this is at, we'll say 1, and that's going to be equal to the ring at 2, potential energy plus kinetic energy, plus the bead at position 2, its potential energy plus its kinetic energy. Now the next thing we need to do is to find the 0 point of gravitational potential energy, and as normal you can apply that, you can decide that to be anywhere. So let me think now, where am I going to put this? What I'll say is the 0 point for the gravitational potential energy is along the wire. Alright, so that means that up here there is no gravitational potential energy, and in this scenario the bead has negative gravitational potential energy, because above the wire is positive and below the wire is negative gravitational potential energy. So let's go ahead and apply the values that we know. So like I said, the potential energies at position 1 are going to be equal to 0. So it's 0 here, plus the kinetic energy, so it's a half m, and the initial velocity of the ring is equal to 0, plus the potential energy of the ring, which was equal to 0, plus once again half m times 0. Alright? Now that's going to be equal to the potential energy of the ring at position 2. So the ring is still on the wire, so it's going to be 0. Plus its kinetic energy, which is going to be half m, and I'm going to say v1 squared. Plus the potential energy of the bead. Now the bead, of course, has negative gravitational potential energy, so I can change this straight away to a negative sign. Then it's the mass times the gravity times the height. Now we're told that the length of the wire is 5 meters, so this is also 5 meters. And finally we have to add its kinetic energy. Now its kinetic energy is negative v1, so we're going to have to say it's negative half, or we could say this, watch, half m times negative v2 to be squared. That's probably the best way to do it. In actual fact, that's the only way to do it. So let's see what we have as a result of that. We have 0 plus 0 plus 0 plus 0 is equal to half mv1 squared minus 5mg plus half mv2 squared. So we're going to cancel across our m's because we no longer need those. And if we multiply across by 2, we'll get that on this side 0 is equal to v1 squared minus 10g plus v2 squared. So we can say that v1 squared plus v2 squared is equal to 10g. Alright, so how do we solve this? Well, we solve this because we know what the relationship between v1 and v2 is. We know that v1 is equal to negative v2. So what we could do here is put in negative v2 squared plus v2 squared is equal to 10g. Alright, so this is 2v2 squared is equal to 10g, v2 squared is equal to 5g, v2 is equal to the square root of 5g. Okay? So the next thing we need to do is just have a look at our calculator. So 5 times 9.81 and square root that answer, and we get an answer of 7 meters per second. So that means the following. I'm just going to write it very explicitly, that v1 is equal to 7 I hat and v2 is equal to negative 7 I hat. Or the other way around, it doesn't really matter. Just one is opposite, one is in actual fact, yeah, that's what that means. Okay, so thanks for watching. Please pass it on to your friends and subscribe to my channel.